The next is scintillation effect. This is a change of irradiance at the receiver, or fluctuation in irradiance at the receiver. And this is caused by the eddies which are of same size as beam size. So basically you get patterns of dark and bright spots here, which are called as speckle pattern. So this is nothing but scintillation effect, and it basically introduces at some places deep fades. If your receiver is close to a place where you have the beam, there's a destructive effect of the beam, then it will result into deep fade, and the performance of the system may get affected. So scintillation index, the whole thing is defined by scintillation index, which is intensity square, or the irradiance square, average of irradiance square, minus you take the average of irradiance and then square, divided by average of I and then squared. So this can be written in this fashion. So this is how scintillation index is defined. And if you see, the intensity or the irradiance is defined by I, and X is the amplitude, and I0 is when there is no turbulence, intensity when there is no turbulence. So I will be defined as I0 exponential 2x minus expected value of x, where x is the amplitude. And if I want to see the effect of scintillation index, that is sigma I square, in terms of sigma I square, that is because of the change in the amplitude, or the variance in the amplitude, they are related by sigma I square is equal to 4x square. And sometimes you take log variance of the irradiance, or log irradiance and then that variance, log irradiance variance, if I take the log of irradiance rather than only the irradiance, that will be defined by a term which is called as sigma r square, which is nothing but right of parameter. So the scintillation index can also be written in terms of log irradiance variance, and this is generally given by exponential sigma r square minus 1. And if this value is 1, this can be equated to sigma r square, because if you have e raised to power x, and if x is small, this can be written as 1 plus x. So this will be equivalent to sigma r square for low value of right of experience, and this is actually weak turbulence effect. So there are two types of waves, plane waves and the spherical waves. So this scintillation index has been defined both for plane waves and spherical waves. So when you have a source and it is emitting in all the directions, so this is, say, for example, R1, this could be R2, let me write a bigger, so this is, say, R1, this could be R2. So if you see, the intensity is average power divided by area. So P average over area if the radius is r in general. So this will be 4 pi r square. And if I see, power at different points defined by this R1 and R2, so I at R1 or divided by I R2, or I1, I2 will be R2 whole square divided by R1 whole square. So when the wavefront is close to the source, it is actually a spherical wavefront. And the energy distribution is given as per this formula. And as wave moves, they tend to become parallel. So these are the rays. So they have plane wavefront. So this is plane waves. This is spherical waves. The scintillation index, sigma I square, as we have seen in the last slide, is equal to relative experience for weak turbulence, is given by 1.23 Cn square. This is the structure constant, refractive index, structure constant, which we had defined earlier. And K is the wave number, which is given by 2 by lambda, and R is the range at distance R. So if you put 2 by lambda here, then you can see that for longer wavelength, there's a lesser irradiance function. So longer wavelength will have lesser scintillation index or lesser sigma I square. This is for plane waves, and this is for spherical waves, which is actually 1 by 4 times less as compared to plane waves. So this is Cn square. So again, refractive index, structure constant, wave number, and distance. So these are the two expressions of scintillation index for plane waves and spherical waves. If I see at strong turbulence, these values are for plane waves and spherical waves for the scintillation index are defined by this. And this is, when your turbulence is very, very high. So, and the sigma r is actually coming at the bottom, which is a function of wave number. And here we will see that smaller wavelengths will have lesser scintillation index in this case. So now let us go to some of the statistical models for received signal irradiance. So there are some well-known models which are defined how which actually tells about the PDF of the irradiance which is received irradiance at the receiver. So one of the well-known model is log normal model, where the radiance, the Fi, the PDF is defined as 1 by 2 pi sigma I square scintillation index. This is irradiance, exponential log natural of I, the average, where mu is divided by 2 sigma I square. So this is the log normal model. This is for weak turbulence, and I can always change this I sigma square if I see the changes in the amplitude and take that variance. So this will be 4 sigma square, and this putting this value of sigma square by 4 sigma square, I can also write in terms of, given by this equation, where it is in terms of the variance which is there in the amplitude of the received signal. So this is for the log normal model for weak turbulence. This cannot be used for, high turbulence, because experimentally we have seen that this model fails when you try to use the same model for high turbulence. So for strong turbulence, the field amplitude is actually really distributed. And this is much greater than 1. So for strong turbulence, this model is not valid, whereas the model which is called as exponential model or the negative exponential statistics model, that is valid because the field amplitude at the receiver is really distributed when you have the strong turbulence. So this Fi, the PDF is given by 1 by I naught. This is without turbulence, exponential minus I by I naught. So this is another model. So we have seen one model which is a log normal model, which is generally valid for weak turbulence, and then for strong turbulence we have another model which is called negative exponential model or negative exponential statistics. There are other models because these models are specifically for some regime, for example weak regime or high regime, but we should have a model which should actually span across the regimes. The same model should work for weak or moderate or high turbulence. So there are, for stronger turbulence, there is a K model. And for models which are valid for all regimes, you have one IK model and gamma gamma model. So let us first see the K model. K model, the PDF is given by this, which is where I and K are the Bessel functions of order alpha, second order Bessel functions of order alpha. And alpha is actually defined as, this is a channel parameter. And this is related to number of discrete scatterers. So this K model is actually only valid for strong turbulence, and when alpha is very high, this gamma function here, when alpha tending to infinity, for example, this gamma function actually becomes a delta function. And this K model will reduce to, under this condition, when alpha is infinite or number of discrete scatterers are many. So under this condition, this gamma alpha will go to delta function, and this K model will become a negative exponential model, which we had discussed in the last slide, negative exponential. So this is K model, and which has a very small regime for high value of turbulence. This model is valid, and this is similar to your K model when alpha is tending to infinity. So it becomes similar to your K model. The other model which is valid for all the regimes is IK model. This here again you see this IK. They are the modified Bessel function of order alpha, and also there are alphas and betas, and alpha and beta are the parameters for. Alpha is basically the eddies which are corresponding to small size, and beta are the eddies which are corresponding to the bigger size. And this row you see here, this row is actually power ratio of mean intensities of deterministic part, that is a fixed part, or the average part, deterministic, and random part. And so this is the PDF for IK model, and as this row tends to 0, which means you have high random part, this model will also reduce to K model, K. This reduces to K model. And they don't have no closed form equation, no closed form. So sometimes it becomes difficult to handle mathematically. So in order to have a model which has a closed form, there is another model which is called as gamma model. And gamma model is basically the PDF is defined by this expression, and where alpha and beta are defined by this. And as you see, alpha is function of chi-square and d square, and these two functions, the chi-square is defined by this. This is important parameter, refractive index structure constant. This is k is the wave number and r is the distance, and this d has wave number, the distance part, as well as the dr, that is the aperture of the received lens. So it involves the cn square, the ri refractive index structure constant, and also indirectly involved lambda, because k wave number is function of lambda, the distance, and the dr, that is the receiver aperture diameter. So this alpha and beta are components which can be calculated based on these parameters given by this equation. So, and this model actually basically depends on, you have two components, which is a why it is called gamma, because one of the gamma is for large eddies, the other is for small eddies, and I, the radiance function, is actually a combination of these two, ix and iy, and this E expected value we can take as 1. So I want to calculate the scintillation index, which by definition is given by this, and if I take expected value of I is equal to 1, then this will change to an EI square. So I'm not calculating this, but there are some standard textbooks, they have calculated this. So expected value of I square is 1 plus 1 over alpha into 1 plus 1 over beta. So by putting expected value of I as 1 and expected value of I square as this, we can calculate the scintillation index, which is actually 1 by alpha plus 1 by beta plus 1 by alpha beta. And alpha beta, is a function of xi, and xi is function of cn square, k, r, and d. Similarly, you have d, that is small d, which has receiver aperture length and the wave number and the distance. So now let us try to understand the effect of atmospheric turbulence on a Gaussian beam. So what happens before that, let us just calculate, sum up the different distributions which you have studied. So if you see those distributions, suppose I have a scale where rho I square is starting from say 0 to 7. I mean, this is a range because 7 is considered as highly turbulent and 0 is considered as no turbulence. So you have 0, 1, 2, 3, 4, 5, 6. So in this range, which is say 0 to 1, in this range, weak turbulence, you have the log normal distribution. And if you see between 3 and 4, somewhere here roughly, which is a high turbulence area, one K distribution is valid. And negative exponential is actually only valid for high turbulence. So basically it starts from somewhere here, 1, and so this is a negative exponential distribution. And IK basically covers all regimes. So this is IK distribution, and it covers high, all regimes starting from weak to high. And similarly, gamma gamma, which has a closed form solution, others have, they don't have closed form solution, so difficult to handle mathematically. So this is gamma gamma, which again spans across different regimes, and it has a closed form solution. So this is widely used. Nowadays, recently one more distribution has come, which is gamma gamma, generalized gamma gamma. Again, it is valid for all regimes of the turbulence. So this is how different models can be used depending upon the value of scintillation index, that is sigma I square. So now let us try to understand what happens to a Gaussian beam as it travels through a turbulent medium. So a Gaussian beam can be represented by, say, UR at R is equal to 0. This is capital R, that is initially. A0 is the amplitude, exponential minus R square. This is the beam width. Minus IKR square, K is the wave number. And F0 is given by, F0 is a phase front radius of curvature, phase front radius of curvature. That depends how you are beam forming. So there are basically three types. One is you have converged beams, converge. The second is collimating. The third is diverging beams. So this F0 actually is for converging beam is greater than 0, and this F0 for collimating is infinite, and is for diverging it is less than 0. So this is a phase front radius of curvature, which actually specifies the beam forming. So just to understand this, different structure which will converge the beam or collimate the beam or diverge the beam. So this is, for example, your beam width, say 2 omega 0, and this is moving in, say, z direction. This is z direction. So the converging beam will behave like this, and the beam ultimately will take this path. This is how the beam will look like, and this is actually F0 for converging. So this here it is f0 greater than 0, and this is first converging, and then as it travels it starts diverging. So this is converging type of beam. The other option is that collimating. Collimating, again, let us see, this is your beam width 2 omega naught, and collimating in this, it goes parallel. This is, so your beam will look like this. It is sort of collimating, almost goes, parallel throughout the distance. Here f0 is infinite. And the third would be let me write omega square 0 here, which is diverging. So this is the z direction, and the beam is diverging. Right, and this is actually f0, which is negative. So this f0 is less than 0 here. So this is how different types of beam forming approaches can be used. So this f0 basically depends whether you have converging or collimating or diverging beams. So this is mentioned here. And at a distance r, the field is equal to a naught. It gets attenuated. And then there's also a phase difference, which is introduced, which is ik given by this ikr. This is at a distance r, that Gaussian beam. And where this capital theta is defined by 1 minus r by f0. This is due to focusing. This is due to focusing. I mean, whether you are using converging or collimating or divergence, due to focusing. And the other capital lambda 0 is because of the diffraction. And here this omega, this W is actually the beam width after a distance r. And this is F, this is at the receiver aperture, this value of phase front radius of curvature at the receiver. So this gets modified as the beam travels a distance of r. And this is represented by E naught r, capital R, and given by this expression, where these are the beam parameters, capital theta and capital lambda naught, defined by these expressions. And if I want to calculate the intensity, it is amplitude square. So I0 is given by amplitude square of the received beam. And if I put, U naught RR and into U conjugate RR and try to see, so this becomes watts per meter square, exponential minus 2r square omega square. This is the beam width at distance r, which has actually increased. Beam width at distance r of the Gaussian beam, which was energized in the beginning, or at r is equal to 0. And this is the reduction in the amplitude which is happening. So I0 RR at r is equal to 0 is given by this formula. And and if I see, let me now draw here itself how the Gaussian beam will look like when it has traveled a distance of r. What are the parameters changing? What is the power which is received at a distance r? Let us try to understand some of those quantities. So as you suppose this is your input Gaussian beam, and this is given by, say, beam width omega 0, and as it travels a distance r, so this beam will actually spread, and this will become omega, that is a distance of r. It has, the beam width has become omega, and so this is the I0 RR, and this was I0 R0. So there is a, because of atmospheric effect, this beam is, the beam width size has increased, and this beam width size actually is roughly, is given by this expression, that is W0 plus R, that is the range, into theta, and theta is your divergence angle. So roughly it is the initial beam width plus r theta, and this theta is given by initial beam width size divided by mod value of f naught. And if I calculate the power at distance r, which is a function of PR, and also it is function of the d, which is the receiver aperture, diameter of the receiver aperture, let me write that as capital D. So the power received PRD at a range r, or at a distance r, is given by d square. P naught was the initial power, divided by 2 into omega 0 plus r theta whole square. So basically it depends on, receipt power depends on your receiver aperture diameter. This was the initial power with which the Gaussian pulse was transmitted, and this is the initial width, and this is the range part, and this is the divergence angle. This whole thing actually gives you increase in the beam width size, and the power received is given by this. So basically at high at a long distance, this beam width gets expanded, so effectively it is introducing a pointing error loss here, and the average power which is sensed by the receiver also reduces. So this is how Gaussian beam behaves under the effect of atmospheric turbulence. Now there is one more concept, actually right-of approximation is valid for weak turbulence. So how to modify this for, so that it can cover high turbulence as well. So there are some assumptions which are made, and we can calculate the rate of approximation, or use rate of approximation for any kind of regime, whether low turbulence or high turbulence or medium turbulence. The assumptions maintained are that those large scale and small scale fluctuations which are happening because of the large scale eddies or small scale eddies, the diffraction happening because of the small scale and the refraction happening because of the large scale, they are independent and they are multiplicative, which is a valid assumption, that is x and y are independent and the total effect is multiplicative. So the total effect is I is equal to xy, and let us assume the average of x and y is they are normalized to 1, and we are also periodically using special frequency filters to account for loss of spatial coherence, because as it travels beam, there is a loss of spatial coherence happening. So this has to be contained, and use of special frequency filter will make the spatial coherence nearly constant. So I square, if I take, because x and y are independent, this is ensemble value of x square and y square, and this is given by 1 plus sigma x square, and for y it is 1 plus sigma y square. And if I put these values in the scintillation index, that is I square ensemble value of I square average divided by ensemble average value of I whole square minus 1 will give me 1 plus sigma square plus 1 plus sigma y square minus 1. And expanding this will give you sigma square plus sigma square y square plus sigma square into sigma y square. Now I want to change this variation in x with log variation in x. So this can be seen that variation in x is related to e raised to power variance in log natural x or log x minus 1. So this can be equated like this, and similarly y square can be equated like this. And if I put these values, sigma I square, that is scintillation index, is equal to exponential the log variance of scintillation index, that is sigma square ln I, this is log natural, minus 1, and putting the value of sigma square log natural for total irradiance is given here, minus 1. And this is the formula for, which handles both small scale as well as large scale turbulence effect. So in case of weak turbulence, basically this sigma square is nothing but sigma square Li, because this becomes, this is e raised to power x, which can be written as, if x is small, as 1 plus x. So using the same thing, this can be written as scintillation index for weak fluctuation is sum of sigma square ln x plus sigma square ln y, where this is x, y is for the large scale turbulence effect, and y is because of small scale eddies or small scale turbulence effect. So this is how, this modified expression can be used for all the regimes, which includes weak turbulence as well as high turbulence. So this is, so far we have understood the effect of turbulence, and then let us try to understand how these turbulence effects can be mitigated. There are different schemes for mitigating the effect of this atmospheric turbulence. So now we will try to understand some 4 or 5 methods by which we can reduce or mitigate the effect of atmospheric turbulence.